find a comfortable position right now. Maybe shift slightly, adjusting your weight so that your body can truly settle. Let your shoulders drop just a little. Notice the weight of your head against your pillow, the gentle pressure of the mattress supporting you. Take a slow breath in through your nose, feeling your chest expand, and then release it gently through your mouth, letting any tension from the day drift away like morning mist dissolving in sunlight. Tonight, we're going on a journey through cosmic space, but this isn't a journey that requires any effort from you. You don't need to remember every number or every fact. Just let the words wash over you like gentle waves on a shore, painting pictures in your mind's eye. We're going to explore the true scale of our home galaxy, the Milky Way, and its place in the universe that stretches beyond imagination. Close your eyes if you'd like, or let them rest softly on a distant point, and allow yourself to drift with these words into the depths of space. Our cosmic address, Finding Home. Before we can understand the Milky Way's place in the universe, we need to know where we are within it. Imagine, for a moment, that you're writing a cosmic address, the kind that would allow someone from across the universe to find our exact location. You'd start with Earth, then our solar system, then work outward through ever larger structures until you've described our position in the whole cosmos. Earth orbits a rather ordinary star we call the Sun, a yellow dwarf star that's been burning steadily for about 4.5 billion years. The Sun is approximately 93 million miles from Earth, a distance we call 1 astronomical unit. Light from the Sun, traveling at 186,000 miles per second, takes about 8 minutes and 20 seconds to reach us. That means when you look at the Sun during the day, you're seeing it not as it is now, but as it was 8.5 minutes ago. You're looking into the past, even at this relatively close distance. Our Sun is one of somewhere between 200 billion and 400 billion stars that make up the Milky Way galaxy. Think about that number for a moment. 400 billion. If you tried to count to 400 billion, counting one number per second without stopping, it would take you more than 12,600 years. Every single one of those stars you're counting represents an actual sun, potentially with its own family of planets orbiting around it. The Sun isn't at the center of the Milky Way. It sits about 26,000 light-years from the galactic center, roughly 2/3 of the way out from the center to the edge. To understand what a light-year means, remember that light travels at 186,000 miles every second. In 1 year, light covers approximately 5.88 trillion miles. So, when we say the Sun is 26,000 light-years from the galactic center, we mean it's about 153 quintillion miles away from the center. That's a 1 with 20 zeros after it. The Sun resides in what astronomers call the Orion Arm, sometimes called the Orion Spur. It's a minor spiral arm, really just a branch connecting two of the Milky Way's major spiral arms. If you could somehow hover above the Milky Way and look down at it, you'd see a beautiful pinwheel structure with graceful spiral arms curving outward from a central bulge. And somewhere in one of those outer arms, in an unremarkable spot, you'd find our Sun along with its family of planets. Our little region of the galaxy is sometimes called the local bubble, a region of space about 300 light-years across where the density of interstellar gas is notably lower than average. This bubble was likely carved out millions of years ago by supernovae, the explosive deaths of massive stars that cleared away much of the gas and dust in our neighborhood. We also sit within something called the local fluff, a small cloud of warm gas that we're currently passing through on our orbit around the galaxy. The Sun moves through the galaxy at approximately 490,000 miles per hour relative to the galactic center. That sounds incredibly fast, and it is by any human standard. At that speed, you could travel from New York to Los Angeles in about 5.5 seconds. But even at this tremendous velocity, the Sun takes approximately 225 million years to complete one orbit around the galactic center. Astronomers sometimes call this period a cosmic year. In the entire history of Earth, our planet has completed only about 20 cosmic years since it formed 4.5 billion years ago. Dinosaurs walked the Earth less than 1 cosmic year ago. Think about what this means. The last time the Sun was at its current position in its galactic orbit, there were no dinosaurs, no flowering plants, no mammals beyond tiny shrew-like creatures. The supercontinent Pangaea was just beginning to break apart. The Sun's journey around the galaxy has taken it through different regions, different stellar neighborhoods, exposing Earth to varying amounts of cosmic radiation and potentially influencing the evolution of life through subtle changes in climate and environment. Our nearest stellar neighbors give us perspective on just how empty space really is. The closest star system to our Sun is Alpha Centauri, a triple star system about 4.37 light-years away, or roughly 25 trillion miles. The fastest spacecraft humans have ever built, New Horizons, which visited Pluto in 2015, travels at about 36,000 miles per hour. At that speed, it would take more than 78,000 years to reach Alpha Centauri. The scale of even our local stellar neighborhood defies our everyday experience. Within about 30 light-years of our Sun, there are roughly 400 stars. Some are smaller and dimmer than our Sun, red dwarfs that will burn for trillions of years. Some are larger and brighter, destined to live fast and die young in spectacular supernovae. Each of these stars has its own story, its own planetary system perhaps, its own unique journey through the galaxy. Yet, even packed with 400 stars, this region of space is predominantly empty. If you could shrink our Sun down to the size of a ping-pong ball, the nearest star would be another ping-pong ball about 680 miles away. Between them would be essentially nothing but empty space. The architecture of the Milky Way. Now, let's expand our view and look at the galaxy as a whole. The Milky Way is what astronomers classify as a barred spiral galaxy. If you could somehow travel outside our galaxy and look back at it from a distance, you'd see a magnificent structure approximately 100,000 light-years across. For context, that means light would take 100,000 years to travel from one edge of the Milky Way to the other. If you somehow boarded a spacecraft that could travel at the speed of light when the ancient humans in Mesopotamia were first developing writing systems 5,000 years ago, you would have covered only 5% of the galaxy's diameter by now. The most prominent feature you'd notice from the outside would be the disk. This is the flat, spinning pancake of stars, gas, and dust that contains most of the Milky Way's visible matter. The disk stretches from edge to edge, approximately 100,000 light-years across, but it's surprisingly thin relative to its width. At the Sun's location, the disk is only about 2,000 light-years thick. To put this in perspective, if the Milky Way were shrunk down to the size of a dinner plate, it would be thinner than a sheet of paper. But the disk isn't uniform. Astronomers distinguish between two components, the thin disk and the thick disk. The thin disk is where most star formation happens today. It contains the youngest stars, including stars like our Sun, along with most of the galaxy's gas and dust. This disk is only about 1,000 light-years thick at our location. The thick disk, by contrast, extends about 3,000 light-years above and below the galactic plane. It contains older stars, formed billions of years ago during the galaxy's more turbulent youth. These stars have higher velocities perpendicular to the disk, bouncing up and down through the galactic plane in their orbits like cosmic yo-yos. Winding through the disk are the spiral arms, those graceful curved structures that give spiral galaxies their characteristic appearance. The Milky Way has 4 major spiral arms: the Perseus arm, the Norma Scutum arm, the Scutum Centaurus arm, and the Sagittarius Carina arm, along with several smaller arm segments. These arms aren't solid structures like the arms of a pinwheel you might hold in your hand. Instead, they're density waves, regions where stars and gas naturally accumulate due to the gravitational effects of the galaxy's rotation. Think of them like traffic jams on a cosmic highway. Cars enter the jam, slow down, then speed up and leave, but the jam itself remains in roughly the same place. Similarly, stars drift into spiral arms, linger for a while, then drift back out, but the arms themselves persist. The spiral arms are where most new stars are born. The increased density of gas and dust in these regions triggers gravitational collapse, leading to the formation of molecular clouds, the stellar nurseries, where stars are born. These regions glow brilliantly in images of the galaxy, illuminated by hot young stars that formed only millions of years ago. Cosmic infants compared to stars like our Sun. At the heart of the Milky Way lies the central bulge, a roughly spherical concentration of mostly older stars spanning about 10,000 light-years in diameter. If you lived on a planet near the center of the bulge and looked up at the night sky, you'd see something extraordinary. The sky would be ablaze with stars, millions of them bright enough to see with the naked eye, perhaps 10,000 times more than we can see from Earth. The night would never truly be dark. There would be enough starlight to read by, enough to cast shadows. The combined light of these stars would illuminate the landscape almost like perpetual twilight. At the very center of the Milky Way, at the heart of the central bulge, lurks something extraordinary. A supermassive black hole called Sagittarius A, pronounced Sagittarius A star. This monster contains approximately 4 million times the mass of our Sun, all compressed into a region of space smaller than the orbit of Mercury around our Sun. The black hole itself is invisible, of course, as its gravity is so strong that not even light can escape once it crosses the event horizon. But astronomers can detect it through its gravitational effects on nearby stars. There are stars that orbit Sagittarius A so closely and so quickly that astronomers have been able to map their orbits over decades of observation. One star, designated S2, completes an orbit around the black hole in just 16 years, traveling at speeds up to 3% of the speed of light at its closest approach. The very existence of these stars orbiting something invisible provided some of the strongest evidence that supermassive black holes really exist at the centers of galaxies. Surrounding the disk and bulge is the stellar halo, a roughly spherical distribution of stars and globular clusters that extends far beyond the visible disk. The halo is much more sparsely populated than the disk. If the disk is a bustling city, the halo is the empty wilderness beyond the city limits. The stars in the halo are ancient, among the oldest objects in the galaxy, formed when the Milky Way was young. These stars have highly elliptical orbits, plunging through the disk and then soaring high above it in great looping paths that can take hundreds of millions of years to complete. Scattered throughout the halo are about 150 globular clusters, dense spherical collections of stars that each contain hundreds of thousands to millions of stars, packed into regions only a few dozen light-years across. These globular clusters are incredibly old, with ages of 12 to 13 billion years, formed when the universe itself was less than a billion years old. They're like time capsules, preserving samples of the primordial gas from which the galaxy formed, allowing astronomers to study conditions in the early universe. But there's more to the Milky Way than meets the eye, literally. Astronomers have discovered that the galaxy is embedded in a much larger halo of dark matter, mysterious invisible substance that doesn't emit, absorb, or reflect light, but makes its presence known through gravitational effects. This dark matter halo extends much farther than the visible parts of the galaxy, perhaps as far as 600,000 light-years or more from the center. Some recent studies suggest the dark matter halo might extend even farther, possibly reaching out to 950,000 light-years from the galactic center, making the complete Milky Way system about 1.9 million light-years across. The existence of dark matter was first inferred from observations of how galaxies rotate. Based on the visible matter in galaxies, stars near the outer edges should orbit much more slowly than stars near the center, just as planets in our solar system farther from the Sun orbit more slowly than planets closer in. But that's not what astronomers observe. Stars at the outer edges of galaxies orbit at roughly the same speed as stars closer to the center. The only way to explain this is if there's additional mass we can't see, distributed in a halo around the galaxy, providing extra gravitational pull that keeps those outer stars moving fast. This invisible dark matter appears to make up about 85% of the total matter in the galaxy. Everything we can see, all the stars and gas and dust, is just the tip of the cosmic iceberg, a journey through galactic distance. To truly appreciate the scale of the Milky Way, let's take an imaginary journey from our Sun toward the galactic center, traveling at the speed of light. Remember, at light speed, you could circle the Earth more than 7 times in a single second. At this speed, you could travel from Earth to the Moon in 1.3 seconds. The entire solar system, from the Sun out to the orbit of Neptune, you could cross in about 4 hours. So, buckle up for our journey to the galactic center. We leave the Sun behind, watching it shrink to a bright point of light. Within hours, we're passing through the outer solar system. Neptune, the outermost major planet, recedes behind us. We cross into the Kuiper Belt, a region of icy objects beyond Neptune's orbit. Then we enter the Oort cloud, a vast spherical shell of dormant comets that marks the true edge of the solar system's influence. This takes us nearly 2 years of travel at light speed. Finally, we emerge into interstellar space, the void between stars. And now we travel. For years, we travel through near-perfect emptiness. The Sun behind us has faded to just another bright star among millions. Ahead, other stars slowly grow brighter as we approach them. After 4.37 years, we pass through the Alpha Centauri system, our nearest stellar neighbor. The 3 stars of this system flash past, their light blazing intensely for a brief moment before receding behind us. We continue. More years pass. We're flying through the Orion Arm now, the region of the galaxy where the Sun resides. We pass stellar nurseries where new stars are being born. nebulae glowing with the light of hot young stars, regions where the gas is so thick it blocks out the light from stars beyond. We pass through clouds of interstellar dust that scatter light in beautiful patterns. We zip past white dwarf stars, the slowly cooling embers of stars that have exhausted their fuel. We skirt around red giant stars, bloated and cool, stars in their old age that have swelled to enormous sizes. After 1,000 years of travel at light speed, we've covered about 1,000 light years, less than 4% of the distance to the galactic center. The Sun is now invisible without a telescope, lost among the countless other stars. The structure of the galaxy is beginning to reveal itself to us. We can see that we're traveling through a flat disk structure, with most stars distributed in a relatively thin plane. 5,000 years into our journey, we're 1/5 of the way to the center. We notice the density of stars gradually increasing. There are more stars per cubic light year here than there were in the Sun's neighborhood. The night sky, if we stopped and looked back, would be noticeably brighter, filled with more stars than are visible from Earth. 10,000 years after we left the Sun, we're approaching the inner regions of the disk. The spiral arms are more pronounced here, denser concentrations of stars and gas. We're passing through regions of intense star formation, areas where massive stars are being born, living their brief lives, and exploding as supernovae, all on timescales of just millions of years. 15,000 years, and the star density continues to increase dramatically. We're now approaching what astronomers call the molecular ring, a region roughly 13,000 to 16,000 light-years from the center that contains a huge concentration of molecular hydrogen, the raw material for star formation. This ring holds a significant fraction of all the gas in the inner galaxy. 20,000 years into our journey, we're entering the inner regions of the galaxy. The stars here are packed much more closely together than in the Sun's neighborhood. If we could stop and look around, we'd see the sky filled with so many stars that it might be difficult to distinguish individual ones. The combined starlight would create a perpetual glow, perhaps bright enough to cast shadows. At 25,000 years, we're plunging into the bulge, the central concentration of older stars. The star density here is thousands of times higher than in the Sun's neighborhood. The gravitational environment is intense, with stars tugging on each other, their orbits complex dances orchestrated by the combined pull of billions of neighbors. Finally, after 26,000 years of travel at the speed of light, we reach the center. We slow down, approaching carefully. The central region is chaotic. Stars zip past at tremendous velocities, their orbits heavily influenced by the supermassive black hole at the absolute center. We can detect X-rays and other high-energy radiation emanating from the region immediately around the black hole. Gas and dust in the area is being heated to tremendous temperatures by the intense gravitational and magnetic fields. And there it is, Sagittarius A. We can't see the black hole itself, but we can see its effects. Stars orbiting at a substantial fraction of the speed of light, their paths warped by the intense gravitational field. Gas spiraling inward, glowing brightly as it's compressed and heated before disappearing forever beyond the event horizon. This is the gravitational anchor of the Milky Way, the object around which 300 billion or more stars ultimately orbit. 26,000 years. That's how long it took us to reach here traveling at light speed, the fastest speed possible in our universe. And remember, we've only traveled from our position 2/3 of the way out to the absolute center. To cross the entire galaxy from edge to edge would take 100,000 years at light speed. Think about what this means for our perception of the galaxy. When we look toward the galactic center from Earth, we're seeing light that left that region 26,000 years ago. Humans were still hunter-gatherers. Cave paintings were being created in Europe, and the last ice age was drawing to a close. The light has been traveling through space all this time, through the entire span of recorded human history and beyond, finally arriving at our telescopes to tell us about events that happened millennia ago. The Milky Way's stellar population. The Milky Way isn't just a collection of stars. It's a complex ecosystem with different types of stars in different regions, stars of different ages and different compositions, all telling stories about the galaxy's history and evolution. Astronomers estimate the Milky Way contains between 200 billion and 400 billion stars. That's a range of uncertainty of 200 billion stars, which itself is more stars than most small galaxies contain. The reason for this uncertainty is simple. We can't count them all. Many are hidden behind clouds of dust, particularly in the direction of the galactic center. Some are too dim to detect even with our best telescopes. And we can only actually see stars in our portion of the galaxy. We can't see through to the far side. These stars come in an extraordinary range of types. The most common stars in the galaxy are red dwarfs, small cool stars with masses between about 8% and 40% of the Sun's mass. These stars are so dim that not a single one is visible to the naked eye from Earth, despite being the most numerous type of star in our galaxy. Red dwarfs burn their hydrogen fuel very slowly, and they'll continue shining for trillions of years. The smallest red dwarfs forming today won't exhaust their fuel until long after the Sun has died, and the universe has aged to dozens of times its current age. Stars like our Sun, sometimes called yellow dwarfs, are actually fairly uncommon in the grand scheme of things. They make up perhaps 5 to 10% of all stars in the galaxy. These stars burn steadily for about 10 billion years, making them stable enough to potentially host life-bearing planets for long periods. At the other end of the spectrum are the massive stars, those with masses 10, 20, 50, or even more than 100 times the mass of our Sun. These stars are rare but spectacular. They burn their fuel so fast that they live only millions of years, sometimes mere hundreds of thousands of years for the most massive ones. They shine with the luminosity of hundreds of thousands or even millions of suns. When they die, they do so catastrophically, exploding as supernovae that for a brief time can outshine entire galaxies. Between these extremes are stars of every intermediate mass: orange dwarfs, white main sequence stars, giant stars, supergiant stars, each category representing a different stage of stellar evolution or a different initial mass. The diversity is staggering. Then there are the stellar remnants, the remains of stars that have finished their normal life cycles. White dwarfs are the fate of stars like our Sun. After they've exhausted their nuclear fuel and shed their outer layers, they leave behind a dense core about the size of Earth, but containing about half the mass of the Sun. These objects slowly cool over billions of years, fading from white-hot to red to eventually black. The galaxy is thought to contain perhaps 10 billion white dwarfs, though most are so dim we haven't detected them. Neutron stars are the remnants of more massive stars that exploded as supernovae. These objects pack 1.5 to 2 times the Sun's mass into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The galaxy might contain around 100 million neutron stars, though we've only detected a tiny fraction of them. And then there are stellar mass black holes, the remnants of the most massive stars. When a star, more than about 20 times the mass of the Sun, ends its life, its core collapses completely, forming a black hole. Astronomers estimate there might be 10 million to 100 million stellar mass black holes scattered throughout the Milky Way. They are nearly impossible to detect unless they are pulling matter from a companion star, causing that matter to glow brightly before it disappears beyond the event horizon. The galaxy also contains numerous multiple star systems. Our Sun is unusual in being alone. Most stars have one or more stellar companions. Binary systems where 2 stars orbit each other are extremely common. Triple star systems like Alpha Centauri are less common but far from rare. There are even systems with 4, 5, or more stars all orbiting each other in complex gravitational dances. And of course, many of these stars have planets. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, astronomers have discovered thousands of planets around other stars. We now know that planets are common, that most stars probably have planetary systems. The Kepler Space Telescope alone discovered more than 2,700 confirmed exoplanets, and suggested that there might be billions of planets in the Milky Way, including potentially billions of Earth-sized planets in their stars' habitable zones, where conditions might be right for liquid water and possibly life. Our galactic neighborhood. The local group. The Milky Way doesn't exist in isolation. It's part of a small cluster of galaxies called the local group, held together by their mutual gravitational attraction. Understanding the local group helps us begin to grasp the scale of cosmic structures beyond individual galaxies. The local group spans about 10 million light-years in diameter. To put this in perspective, remember that the Milky Way is about 100,000 light-years across. So the local group is roughly 100 times wider than our galaxy. Yet the local group itself is relatively small in the cosmic hierarchy of structures. It's just a modest collection of galaxies in what turns out to be an increasingly vast universe. The local group contains more than 80 known galaxies, though new, very faint dwarf galaxies are still being discovered as observational techniques improve. The total number might eventually prove to be over 100 once we account for all the dim, difficult to detect dwarf galaxies. But the local group is dominated by 3 large galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The Andromeda Galaxy, also called Messier 31 or M31, is the largest member of the local group. It's a spiral galaxy like the Milky Way, but somewhat bigger in most respects. Andromeda contains roughly 1 trillion stars, about 3 times as many as the Milky Way. Its spiral disk spans about 220,000 light-years, more than twice the diameter of the Milky Way's disk. If you could somehow see Andromeda's full extent in the sky, it would appear about 6 times wider than the full moon, even though it's 2.5 million light-years away. Despite its distance, Andromeda is actually visible to the naked eye from a dark location. It appears as a faint, fuzzy patch of light in the constellation Andromeda. When you look at it, you're seeing light that has been traveling through space for 2.5 million years. When that light began its journey, our distant human ancestors were just starting to use stone tools. Modern humans, Homo sapiens, didn't even exist yet. The light you're seeing predates our entire species. Andromeda is moving toward the Milky Way at about 68 miles per second, or roughly 250,000 miles per hour. This might seem fast, but at this speed it would still take more than 6 billion years for the galaxy to reach us, even though it's already one of our closest neighbors. When people say Andromeda and the Milky Way are on a collision course, they're not exaggerating, but they're also talking about something that will happen in the far distant future, billions of years from now. The third major member of the local group is the Triangulum Galaxy, also called Messier 33. This spiral galaxy is smaller than both the Milky Way and Andromeda, containing perhaps 40 billion stars. It lies about 3 million light-years from us, making it slightly farther away than Andromeda. Triangulum has a disk about 60,000 light-years across, making it roughly half the size of the Milky Way. It's gravitationally bound to Andromeda and may actually be a satellite galaxy of Andromeda, though this isn't certain. Beyond these three large spirals, the local group consists mostly of dwarf galaxies. These are much smaller systems, often irregular in shape, containing anywhere from a few million to a few billion stars. Many of these dwarf galaxies are satellites of either the Milky Way or Andromeda, orbiting around the larger galaxies much like the Moon orbits Earth. The Milky Way has dozens of known satellite galaxies. The most prominent are the Large Magellanic Cloud and the Small Magellanic Cloud, visible to the naked eye from the southern hemisphere. The Large Magellanic Cloud contains perhaps 30 billion stars and lies about 160,000 light-years away. It's so close in cosmic terms that detailed studies of individual stars within it are possible with modern telescopes. The Small Magellanic Cloud is smaller and more distant, containing a few billion stars and lying about 200,000 light-years from us. Other Milky Way satellites include the Sagittarius Dwarf Elliptical Galaxy, currently being torn apart by the Milky Way's tidal forces as it passes through our galaxy's disk. There's the Sculptor Dwarf Galaxy, the Fornax Dwarf Galaxy, the Carina Dwarf Galaxy, and many others, most named after the constellations in which they appear from our perspective. Many of these were only discovered in the late 20th century, and astronomers continue to discover new ones. These satellite galaxies have important implications for our understanding of galaxy formation and evolution. Many of them are in the process of being cannibalized by the Milky Way, their stars gradually being stripped away and incorporated into our galaxy's halo. This ongoing process of merger and accretion is thought to be fundamental to how large galaxies like ours grow over cosmic time. The arrangement of galaxies in the local group isn't random. The Milky Way and its satellites form one gravitational subsystem, while Andromeda and its satellites form another. These two subsystems orbit around their common center of mass, which lies somewhere between them. In the far future, these two subsystems will merge, creating one massive galaxy from what are currently dozens of separate systems. Beyond the local group, cosmic structures. The local group itself is just one small component of progressively larger structures in the universe. As we zoom out further, we begin to see the truly large-scale organization of matter in the cosmos, structures so vast that they strain our ability to comprehend them. The local group resides on the outskirts of what astronomers call the Virgo cluster, an enormous collection of galaxies about 54 million light-years from us in the direction of the constellation Virgo. The Virgo cluster contains roughly 1,500 to 2,000 galaxies, ranging from giant ellipticals containing trillions of stars to small irregular dwarfs with only millions. The cluster is dominated by a massive elliptical galaxy called Messier 87, which sits near the cluster's center and contains about 1 trillion stars. This galaxy also hosts one of the most massive, supermassive black holes ever discovered, with a mass of about 6.5 billion times the mass of our Sun. The same black hole captured in the famous first-ever image of a black hole released in 2019 by the Event Horizon Telescope collaboration. The Virgo cluster is itself part of the Virgo supercluster, also called the local supercluster, a large-scale structure spanning about 110 million light-years. The Virgo supercluster contains at least 100 galaxy groups and clusters, and probably between 10,000 and 50,000 galaxies in total. The Milky Way lies in a relatively sparse region of this supercluster, far from the densely packed central region where the Virgo cluster resides. For many years, astronomers thought the Virgo supercluster defined the largest gravitationally connected structure containing our galaxy. But in 2014, a team of astronomers led by R. Brent Tully redefined our place in the cosmic structure. Using new techniques to map the velocities of galaxies throughout our region of space, they discovered that what we thought was the extent of our local supercluster was actually just one part of an even larger structure. They called this newly defined structure Laniakea, a Hawaiian word meaning immense heaven or open skies. The name honors Polynesian navigators who used their knowledge of the heavens to voyage across vast stretches of the Pacific Ocean. Laniakea encompasses approximately 100,000 galaxies spread across a region about 520 million light-years in diameter. It has a total mass roughly 100,000 times the mass of the Milky Way. Laniakea is defined not by the locations of galaxies, but by their motions. In particular, all galaxies within Laniakea are flowing toward a common center of mass called the Great Attractor, a region of extraordinarily high galaxy density, located roughly 200 million light-years from us. The Great Attractor isn't a single object, but rather a massive concentration of galaxy clusters whose combined gravitational pull influences the motion of galaxies across hundreds of millions of light-years of space. The structure of Laniakea is fascinating. It consists of several previously defined superclusters: the Virgo supercluster, where we reside, the Hydra Centaurus supercluster, the Pavo Indus supercluster, and the Southern supercluster. These are all flowing toward the Great Attractor, their motions orchestrated by gravity acting across immense distances. But even Laniakea isn't the end of the story. More recent observations suggest that Laniakea itself, along with several other nearby superclusters, may be flowing toward an even larger concentration of matter called the Shapley concentration, or Shapley Attractor. This structure, located about 650 million light-years from us, contains some of the most massive galaxy clusters known and may define a basin of attraction even larger than Laniakea. If this is confirmed, then our cosmic address extends to an even more immense structure, perhaps encompassing 10 times the volume of Laniakea. These superclusters aren't isolated islands in space. They're connected by filaments, long chains of galaxies and galaxy groups that stretch across hundreds of millions of light-years. Between the filaments lie enormous voids, vast regions of space that contain few, if any, galaxies. These voids can be 300 to 500 million light-years across, enormous bubbles of near emptiness in the cosmic structure. When astronomers map the distribution of galaxies across large volumes of space, The pattern that emerges is often called the cosmic web. It resembles a three-dimensional spider web, with dense nodes where clusters and superclusters reside, connected by filaments along which galaxies are strung out, with vast voids between the filaments. This web-like structure is thought to trace the distribution of dark matter, the invisible substance that makes up most of the matter in the universe. Galaxies form where dark matter is most densely concentrated, following the underlying architecture laid down by dark matter in the early universe. The cosmic web is one of the largest known structures in the universe, but it's not perfectly uniform. Some structures are larger than others. The largest structure discovered so far is something called the Hercules Corona Borealis Great Wall, the immense concentration of galaxy clusters stretching approximately 10 billion light-years across. To give you a sense of this scale, light takes 10 billion years to cross this structure. The structure is so large that some cosmologists question whether it's consistent with our theories about how the universe should be structured on its largest scales, the observable universe and our place now. Let's step back and consider the truly largest scale, the observable universe itself, the complete sphere of space from which light has had time to reach us since the Big Bang. The universe is currently about 13.8 billion years old. You might think this means the observable universe is 13.8 billion light-years in radius, but it's actually much larger than that due to the expansion of space itself. While light has been traveling toward us for 13.8 billion years, the space through which it traveled has been expanding all that time. As a result, the distant galaxies whose light we're now receiving are currently much farther away than 13.8 billion light-years. Current measurements indicate that the observable universe extends to about 46.5 billion light-years in every direction from us. The complete observable universe is therefore a sphere roughly 93 billion light-years in diameter. This doesn't mean the entire universe is only this size. The universe may extend far beyond what we can see, perhaps infinitely. But this 93 billion light-year sphere represents the limit of what we can observe in principle, the portion of the universe from which light has had time to reach us. Within this vast volume, astronomers estimate there are approximately 200 billion to 2 trillion galaxies. That's an enormous range of uncertainty, a factor of 10 between the low and high estimates. The uncertainty comes from the difficulty of detecting very distant, very faint galaxies, and from the challenge of counting galaxies that are hidden behind dust in our own galaxy, or that blend together at great distances. Let's think about what 2 trillion galaxies means. If the Milky Way is typical, containing perhaps 300 billion stars, then 2 trillion galaxies would contain something like 600 billion trillion stars total. That's a 6 with 23 zeros after it. If you tried to count all those stars, even counting 1 million stars per second, it would take you roughly 19 million years to finish counting. Each of those galaxies, spread across the observable universe, is its own island universe. Each contains billions or trillions of stars. Each has its own history, its own story of formation and evolution. Some are grand spirals like the Milky Way and Andromeda. Some are elliptical galaxies, smooth-rounded collections of old stars with little gas or dust and minimal star formation. Some are irregular galaxies, lacking any clear structure. Some are tiny dwarf galaxies. Some are giant ellipticals larger than anything in the local group. When we look at very distant galaxies, We're seeing them not as they are now, but as they were when the light left them. A galaxy 5 billion light-years away is being seen as it existed 5 billion years ago, when the Earth was forming from a disk of dust and gas around the young sun. A galaxy 10 billion light-years away is seen as it was 10 billion years ago, when the universe was only about a quarter of its current age. The most distant galaxies we can detect, at distances of 13 billion light-years or more, are being seen as they existed when the universe was less than a billion years old, not long after the first galaxies formed. This means that when we survey the distant universe, we're also surveying cosmic history. We're seeing galaxies at different stages of their evolution, from ancient galaxies in the early universe to more mature systems at intermediate distances, to the fully evolved galaxies in our cosmic neighborhood. It's like looking at a photo album of the universe's development, but with all the photos arranged spatially around us based on how far away they are. Now, where does the Milky Way fit in this enormous cosmic structure? In some ways, the Milky Way is unremarkable. It's a medium-sized spiral galaxy, larger than most galaxies, but far from the largest. It contains hundreds of billions of stars, but some giant elliptical galaxies contain 10 times as many. It's in a relatively quiet region of space, part of a small galaxy group rather than a dense cluster. But, in another sense, the Milky Way is exactly where we should expect to find ourselves. Most of the universe is empty space. Most matter is concentrated in the filaments and nodes of the cosmic web. Among galaxies, most are small dwarfs rather than large spirals. The fact that we find ourselves on a planet orbiting a stable star in a large spiral galaxy probably isn't a coincidence. These are the kinds of places where complex chemistry can develop over billions of years, where stable planetary systems can persist long enough for life to evolve. The Milky Way represents perhaps the top 5% of galaxies by mass. It's forming new stars at a moderate rate of about 2 to 3 solar masses per year, enough to keep the galaxy alive and dynamic, but not so much that it will exhaust its gas supply quickly. It has avoided major mergers for several billion years, allowing its disk structure to settle into a relatively stable configuration. These conditions have been favorable for the development of planetary systems like our solar system, systems that have remained undisturbed long enough for life to arise and evolve. Consider the alternatives. If we lived in a dwarf galaxy, there would be fewer heavy elements available, as these galaxies have had less star formation and fewer supernovae to create elements beyond hydrogen and helium. This might make the formation of rocky planets like Earth less likely. If we lived in a giant elliptical galaxy, we'd probably be surrounded by old stars with few planets, and the high density of stars might lead to frequent gravitational disruptions of planetary systems. If we lived in the dense core of a large galaxy cluster, our galaxy would be constantly harassed by interactions with neighboring galaxies, potentially disrupting the stable environment needed for complex life to develop. The Milky Way's position in the cosmic web, in a relatively low-density region far from massive galaxy clusters, may be crucial for habitability. The rate of mergers and interactions is low enough that our galaxy has had billions of years of relative peace. The density is high enough that the galaxy has plenty of raw material for star formation, but not so high that the environment is violently disturbed by frequent galaxy collisions, time, and the Milky Way's evolution. To truly understand the Milky Way, we need to consider not just its current state but its history and future, the deep time scales on which galaxies evolve. The Milky Way formed roughly 13.6 billion years ago, only about 200 million years after the Big Bang itself. At that time, the universe was a very different place. It was smaller, denser, and hotter. Most of the matter in the universe was still in the form of primordial hydrogen and helium, created in the first minutes after the Big Bang. There were no heavy elements yet. No carbon, no oxygen, no iron. These elements would have to be created in the cores of stars and dispersed by supernovae before rocky planets like Earth could form. The first structures to form in the universe were small dark matter halos, regions where dark matter had collapsed under its own gravity. Visible matter, drawn in by the gravity of these dark matter halos, began to collect and form the first stars and the first small galaxies. The Milky Way probably began as several of these small protogalaxies that merged together in the early universe. The process of galaxy formation wasn't smooth or gradual. It was violent and chaotic. Small galaxies collided and merged, their stars and gas mingling to form larger systems. Each merger would have heated the gas, triggering bursts of star formation as shock waves compressed the gas and caused it to collapse. The resulting young massive stars would have lived fast and died young, exploding as supernovae that enriched the gas with heavy elements and triggered more star formation. Over the first few billion years of the Milky Way's existence, much of its stellar halo was built up through this process. The old stars we see in the halo today and the ancient globular clusters scattered through the halo are remnants of this early epoch of galaxy formation. They're survivors from the Milky Way's violent youth, formed before the galaxy settled into its current disk structure. Around 10 to 11 billion years ago, the Milky Way experienced what astronomers call the thick disk formation epoch. A series of major mergers, including one particularly significant merger with a dwarf galaxy that astronomers have nicknamed Gaia Enceladus, disrupted the early disk and created what we now call the thick disk. The stars from these mergers, along with stars formed in the burst of star formation triggered by the mergers, now populate the thick disk that extends several thousand light-years above and below the current thin disk. After these major mergers ended, the Milky Way entered a quieter phase. Gas that had been heated and dispersed by the mergers gradually cooled and settled into a rotating disk. Star formation continued, but in a more organized fashion, concentrated in this disk. This is the thin disk we see today, the flat structure containing most of the galaxy's gas and current star formation. The Sun formed in this disk about 4.5 billion years ago, a relative newcomer to a galaxy that was already ancient by that point. But the Milky Way's evolution didn't stop when the thin disk formed. The galaxy has continued to grow and evolve. Small dwarf galaxies have been captured by the Milky Way's gravity and torn apart, their stars added to the galactic halo. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is currently being disrupted in this way. Streams of stars stripped from this galaxy wrap around the Milky Way multiple times, telling the story of its orbital motion as it's gradually consumed by our galaxy. The Milky Way has also continued to accrete gas from the intergalactic medium. High-velocity clouds of hydrogen, moving at speeds different from the normal rotation of the disk, are continually falling into the galaxy. Some of these clouds may be pristine material left over from the early universe, never before incorporated into a galaxy. Others may be gas, blown out of the Milky Way by past bursts of star formation, now falling back. This ongoing accretion provides fresh fuel for continued star formation. Currently, the Milky Way is still forming stars at a moderate rate, converting about 2 to 3 solar masses of gas into stars every year. At this rate, the galaxy will exhaust its current supply of star-forming gas in several billion years, unless it continues to accrete more gas from outside. The rate of star formation has actually decreased over the Milky Way's history. 10 billion years ago, the galaxy was forming stars at a much higher rate, perhaps 10 to 20 times the current rate. The peak of star formation in the universe as a whole occurred about 10 to 11 billion years ago, when the universe was 2 to 3 billion years old. Since then, star formation has been declining as galaxies exhaust their gas supplies and as the expansion of the universe spreads matter more thinly. But the Milky Way's relatively peaceful present won't last forever. The galaxy is on a collision course with Andromeda, and this impending merger will fundamentally transform both galaxies. Current observations indicate that Andromeda and the Milky Way will collide in about 4 billion years, though there's considerable uncertainty in this estimate, with some models suggesting it could happen in as little as 3 billion years, or as long as 5 to 6 billion years. When the collision happens, it won't be like a car crash where two solid objects smash into each other. Galaxies are mostly empty space. The stars are so far apart that even when the two galaxies merge, direct collisions between individual stars are extremely rare. Instead, it's the gravitational interactions that matter. As Andromeda approaches, its gravity will distort the Milky Way's structure. Tidal forces will pull stars and gas out of the disk, creating long streams and tails of material stretching into space. On the first pass, the two galaxies will likely interpenetrate, with each passing through the other. But gravity will pull them back together for a second collision, and then a third. Over hundreds of millions of years, the two galaxies will merge, their disks shredded by gravitational interactions, their gas clouds colliding and triggering tremendous bursts of star formation. The process will convert spiral galaxies into something else, probably a large elliptical galaxy. The supermassive black holes at the centers of each galaxy will eventually sink to the center of the merged system, orbiting each other and emitting gravitational waves before finally coalescing into a single, even more massive black hole. The new galaxy, already nicknamed Milkomeda by astronomers, will be a giant elliptical containing the stars from both the Milky Way and Andromeda, roughly 1 trillion to 1.5 trillion stars in total. This might sound catastrophic, and in a sense it is for the galactic structures. But for individual stars and planetary systems, the merger will likely be relatively benign. The solar system, if it still exists by then, will probably survive the merger intact. The Sun will have become a red giant by this point, having exhausted the hydrogen in its core and swelled to perhaps 100 times its current size, likely engulfing Mercury and Venus and possibly Earth. But the planets that remain, and any life that might still exist on moons in the outer solar system, will simply find themselves orbiting in a different galaxy, under a night sky filled with many more stars than we see today. After the merger, star formation in the new Milkomeda galaxy will eventually cease. The violent interactions during the merger will trigger an intense starburst, using up much of the available gas in a final frenzy of star formation. But once that gas is exhausted, and without continued infall of new material, star formation will end. The galaxy will become a stellar graveyard, filled with old red dwarf stars slowly fading, white dwarfs cooling toward black, and stellar remnants orbiting in the darkness. But even this isn't the ultimate fate of the galaxy. On even longer timescales, trillions of years into the future, the galaxy will continue to evolve in surprising ways. Stars will occasionally be ejected from the galaxy through gravitational interactions, slowly eroding the system. Other stars will spiral inward, eventually being swallowed by the central supermassive black hole. The white dwarfs and neutron stars and black holes that make up the galaxy's population of stellar remnants will occasionally collide, creating brief flashes of light in an otherwise dark galaxy. Eventually, many trillions of years in the future, the galaxy might be disrupted entirely by the accelerating expansion of the universe. Recent observations indicate that the expansion of space is not just continuing but speeding up, driven by something called dark energy. If this acceleration continues indefinitely, it could lead to a Big Rip scenario where the expansion becomes so rapid that it overcomes gravity on smaller and smaller scales. First, galaxy clusters would be ripped apart. Then individual galaxies. Eventually, even stars and planets could be torn apart. This scenario is highly speculative, but it represents one possible ultimate fate for cosmic structures. Alternatively, if the expansion doesn't accelerate indefinitely, the galaxy might simply disperse over extremely long timescales as the last stars fade, leaving only black holes orbiting in the darkness. Even these black holes won't last forever. Stephen Hawking showed that black holes slowly evaporate through a quantum mechanical process, emitting what's now called Hawking radiation. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate completely. The supermassive black holes at galaxy centers would take even longer. But given enough time, even these would eventually disappear, leaving nothing but a thin gruel of elementary particles spreading ever more thinly through an expanding universe. These timescales are so long they defy comprehension. The current age of the universe, 13.8 billion years, is utterly insignificant compared to the timescales on which black holes evaporate. But they remind us that nothing in the Sci-Tomb universe is truly eternal. Even structures as grand as galaxies are temporary, islands of order in a universe that's slowly evolving toward maximum entropy. Closing. Perspective and wonder. Let's bring ourselves back now, back from those unimaginable timescales in the far future, back from the edges of the observable universe, back through the cosmic web and the superclusters, back through the local group, back into the Milky Way, through its spiral arms and clouds of gas and dust, back to our sun and our solar system, back to Earth. You're here now, in this moment, lying comfortably as these words wash over you. You exist at a very special time in cosmic history, a time when stars still shine, when galaxies are still forming and evolving, when the universe is filled with structure and light. You exist in a very special place, a planet orbiting a stable star in a large spiral galaxy, a place where the conditions are right for complex chemistry, for liquid water, for life. The Milky Way stretches overhead when you look up on a dark night, a pale band of light crossing the sky. That light comes from billions of stars, each one a sun like ours, many of them with planets, some of those planets perhaps harboring life. You're seeing the edge-on view of our galactic disk, looking through the thickness of the galaxy from our position within it. The light from those distant stars has traveled for thousands of years to reach your eyes, a gift from the cosmos delivered after journeying through the vastness of space. Every atom in your body was forged in the heart of a star, or in the explosion of a star that died before our sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar nucleosynthesis, created by nuclear fusion in stellar cores and distributed through space by supernovae. You are, quite literally, made of stardust, a way for the cosmos to know itself, to reflect upon its own existence. The Milky Way is our home on the largest scale, our cosmic dwelling place in a universe of galaxies. It's a structure of almost incomprehensible size, spanning 100,000 light-years, containing hundreds of billions of stars, weighing as much as 1,000,000,000,000 suns. Yet it's just one galaxy among trillions, an ordinary spiral in an ordinary region of space, neither particularly large nor particularly small, neither particularly old nor particularly young. And yet it's extraordinary in at least one way. It's where you are. It's the galaxy that formed from the primordial fluctuations in the early universe, that grew through mergers and accretion, that created generations of stars which created the heavy elements needed for planets and life, that eventually produced a solar system with a planet in the habitable zone, where liquid water could exist, where life could arise, where evolution could produce beings capable of wondering about their place in the cosmos. You've traveled far tonight in your imagination, from the sun's neighborhood to the galactic center, from the local group to the edge of the observable universe. You've journeyed through 13.8 billion years of cosmic history, from the Big Bang to the present, and glimpsed possible futures billions of years hence. All of this exists. All of this is real. All of this is the universe we inhabit. Now let yourself rest in that knowledge. The universe is vast beyond comprehension, but you're here, now, part of it all. The same forces that shaped galaxies shaped you. The same matter that makes up stars makes up your body. The same laws that govern the cosmos govern the beating of your heart. Take one more slow breath. Feel your body relaxing, sinking deeper into rest. The cosmic journey is complete for tonight. The Milky Way will still be there tomorrow, spinning slowly through space, home to countless stars and worlds and perhaps countless other beings looking up at their own night skies and wondering about their place in it all. If you've enjoyed this journey through space and time, if you found peace or wonder or knowledge in these words, please consider liking this video and subscribing to the Science Pillow. We create these cosmic journeys to help you relax, to help you drift into sleep, and to fill your mind with the wonders of the universe. There's so much more to explore, so many more stories to tell about our cosmos and our place within it. Until next time, rest well. Dream of stars and galaxies, of the vast spaces between them and the intricate structures that fill the universe. Dream of a cosmos that's stranger and more beautiful than we can imagine, and remember that you're part of it all, a conscious mind arising from stardust, looking back at the universe and finding wonder. Good night.